Hello, everybody, and welcome to the Consulting Specifying Engineer webcast, Selective Coordination for Generators and Transfer Switches. Sponsored by ASCO, I'm your moderator, Michael Ivanovich, President of the Ivanovich Group. Part 1 will describe how generators and automatic transfer switches are involved in the selective coordination process, and Part 2 will provide examples and more detailed guidance on selective coordination of hospital systems, including ones currently required by codes and standards. Here's the agenda. Each speaker will present for about 20 minutes and then take your questions. We can extend the length of the webcast to allow for more questions, so feel free to stay on longer for the Q&A. I'm now happy to introduce our two distinguished speakers. Leading off is Jim Ferris. Jim is an associate and electrical project engineer in the healthcare division of TLC Engineering for Architecture in Orlando. He's a professional engineer who has more than 11 years' experience in electrical design for hospitals. A registered engineer in Florida and New York, Jim chairs the Institute of Electrical and Electronics Engineers, Central Florida chapter, and he has a bachelor's degree in electrical engineering from SUNY Binghamton, New York, and a master's in electrical engineering from Polytechnic University in Brooklyn. Speaking second is Dean Erickson, PE and lead AP, who is principal and project manager at Affiliated Engineers, Incorporated. With 27 years of electrical engineering and project management experience, Mr. Erickson has been involved in all phases of facilities projects, from conceptual design to construction supervision. His expertise in electrical and information technology systems includes power distribution systems, lighting systems, security, telephone, process control, and data communication systems. So I'm really pleased to have Jim and Dean with us today. And Jim, let's start with you.
Okay, thank you, Michael. I'm here, this is Jim Ferris with TLC Engineering, and I'm here to give a presentation about emergency power supply systems, coordination and protection, with an emphasis and focus on the generator system and protection. Some of the things that we're going to discuss as part of this presentation is, the first step is we're going to talk about the generator and the alternator data sheet, and kind of go through what are the key components that are on the alternator data sheet and explain some of those components and what they mean. We're going to talk a little bit about permanent magnet generators and what kind of effect they have on your protection and coordination. Then we're going to go into fault calculations for your generators, how to take that alternator data and calculate the fault for your generator, and also look at how that impacts on a multi-generator system. And finally, we're going to go into the actual coordination of the protection with the generator. That includes the damage curve, the decrement curve, and how to really lay out your breakers so that they allow the system to function properly. Now, there's several codes out there that do require selective coordination, especially on the emergency side. NEC is one of those, and what it talks about is you want to localize an outage to the appropriate breaker, and this is taken from the NEC exactly, so you could take a look at that. I'll go into an example in a little bit. Also, one thing to keep in mind from a generator standpoint is that NFPA 110, which is the standard for emergency and standby power systems, includes a requirement that the EPSS must be selectively coordinated as well. Okay, so now we're looking at a simple one-line diagram, and the first question that comes to mind is, why should this system coordinate? The reason why a system would have to coordinate is that if you had a fault on a downstream transfer switch or breaker somewhere down in the system, you don't want that fault to trickle through the system and affect and trip a higher level breaker to affect other loads. And in this case, we wouldn't want it to trickle up to the generators and to knock the generator offline. And then, because knocking the generator offline would obviously affect other loads. So what we're looking at here is if we had a fault on the load side of ATS EQ, we would want the breaker that feeds ATS EQ to react first before the generator breaker reacts. If were the generator breaker to be the one that picks it up, it obviously would affect ATS TR. The way that we demonstrate selective coordination would be to putting all these breakers onto a time current curve format and showing how that plots. And we do go into a couple of those curves later on in the presentation. So this is what I'm talking about. If there's an 800 amp ATS, we would be able to, the 800 amp ATS EQ, we want to make sure that that 800 amp breaker coordinates with the 2500 amp breaker serving the generators. So when you're doing a coordination on an emergency system, you have to start with the generator. The first thing you need to do is to get the parameters for the generator, model the generator, and then start your coordination. If you start down at the lowest level, at your 120, it may all be changed by the time. Once you put in that generator, it may change everything. So the first thing you need to do is model your generator, and then work your way down the system. Now that's contrary to what you might do on a normal utility side, because on a normal utility side, your breakers are not constrained to, in this case, the generator curve. They're not constrained to that. They're not constrained to the utility. They can go all the way out to max. So in order to start with the generator, what we need to do is get the alternator data sheet. Now, all the major manufacturers for whatever engine you may be looking at or specifying or even looking at in the field can provide the data sheet for that particular engine. In that case, that particular alternator. So here's an example of an alternator data sheet. And at first glance, it's pretty overwhelming. And you kind of look at all the different parameters. There's just so much information on it, and it's very technical. So I'm going to break it down and kind of break it out and show you what it's all about. There are some key components that you would need to take a look at. The first one would be the unit data, and then also you would need to take a look at the temperature rise, the generator full load current, and then finally the subtransient reactance. I saved that one for last because that one's a little bit more complicated. We'll get into that in depth. So the unit data, why is that important? That gives you all your basic information, such as your generator model information, what the voltage is, how many phase it is, what's the kW, the kVA, and the power factor. All that boilerplate standard information that you need to know about the generator. The temperature rise. Temperature rise is important because it'll affect the size of your alternator. You can specify a alternator that has, let's say, an 80-degree rise versus 150-degree rise. Now the difference is that, let's say you had an alternator that produces 2,000 kW at 150 degrees. Well, that same alternator might produce 1,500 kW at 80 degrees. And this is all manufacturer-specific information, but you need to be aware of that because if you're specifying alternators that have a low temperature rise, you're actually going to get a bigger alternator. What that does is affects your fault current that's available from that alternator. If you think about it in terms of, the spinning alternator and the mass that is there with the energy that is available when you have a fault, with a larger alternator, you're obviously going to have a lot more mass and a lot more spinning energy. That when you have the fault, that instantaneous moment, you can actually push a lot more fault out onto the bus. So it's important to note what the temperature rise that you're calling for, and keep in mind that it will affect the fault output. The full load current of the generator is the next big item. Now, obviously, here we're looking at a 1,500 kW generator. So this is the rated current that the unit can produce, and it's always tied to the temperature that we're talking about. In this case, we're talking about an 80-degree rise with 2255 amps for that generator. The final major value is the subtransient reactance. and it's X double prime B is what it's identified as. This parameter is an important parameter. It basically is tied to the first 5 cycles or so of the generator performance, which is your fault output of the generator. And it's put in per unit value, so it would be it's not a straight number. It's based upon what the generator kW is and all that. So these are some other values that are available on that sheet, which you do need to keep in mind and you do need to look at as far as variables that you're going to need in order to model the decrement curve appropriately in the coordination modeling software. Okay, so the generator fault output is totally based on the subtransient reactance. And then the fault current beyond that subtransient period is typically based upon whether or not you have a permanent magnet exciter on your generator or not. And what a permanent magnet will do, we'll get back to the permanent magnet in a second. Okay, so let's go into the subtransient reactance. It's a scary word, I know, but it really is a pretty simple concept. Subtransient reactance is basically if you take the current, the full load amps of the generator, you divide it by the subtransient reactance, you get what the fault output of that generator is. It's actually it's a very basic equation with a scary word, but it's pretty straightforward. So if we take an example for this unit that we're looking at, a 1500 kW generator at 2255, and you remember that our XD double prime was 0.113 on the alternate data sheet, that gives me the fault output of about almost 20,000 amps. So I mean, it's a pretty simple equation to remember to actually get what the fault output. And you could actually take that fault output and compare it to what the manufacturer's data sheets would say, and they'll line up. Okay, now the important thing to consider from a multi-generator fault is that you may have all generators operating at one time and all contributing to the bus. So if you had a downstream fault south of the generator breakers, you would actually combine up the fault from those multiple generators. So in this case, I mean, if you had 5 generators of this type on one system, you're producing almost 100,000 amps of available fault current. Now, I'm not including wire losses and I'm not including motor contributions in that. I'm just, as a general rule of thumb, you're pretty much looking at a good amount of fault, which, as you'll see Dean get into in the next slides, does affect the size of your ATSs and the AIC ratings of those units. Okay, so back to the PMG. So the PMG, what the benefit of a PMG is from a coordination standpoint is that the PMG will boost your fault current during a fault event to 300% of your full load amps. If you could look at this TCC, we have 2 of identical generators, one with PMG and one without PMG. As you can see with the blue line, which is the non-PMG, it starts out at the same level, but it decays very rapidly. And when you're talking about selective coordination and allowing the breakers to trip downstream, you want to make sure that you do maintain a certain amount of fault for those breakers to react to. So the PMG on the system is actually pretty important from that standpoint. So we typically specify PMG for all of our healthcare and larger jobs, and I know most manufacturers typically standardize around PMG on the larger engines. Okay, so let's get into coordination. So the goal of coordination is to allow the downstream breakers, that breaker that feeds the ATS EQ, to trip before the generator is taken offline. But at the same time, we want to make sure that our generator breakers, they're there to protect the generator. So we want to make sure that that's what they do. So that's, I mean, it's pretty straightforward goals, but that's it. So here's that example again that we talked about earlier, where we have the fault downstream going through an 800 to the 2500. So we want to make sure that the 800 trips before the 2500, and that 2500 will protect the generator. Okay, so there's the goals. Okay, so there's two curves that are important when you take a look at coordination with the generator. There's the damage curve, there's the decrement curve. The damage curve is the first one we'll look at. Basically, there's a lot of different names for it. You can call it the withstand curve, the overload curve, the thermal damage curve. And this curve is available from the manufacturers. When you get the alternating data sheet, typically you can ask for this information. The damage and the decrement curves are both available from the manufacturer. And then you have to model it and coordinate around it. So they can provide it. Now, typically this is shown as a percentage or a per unit value of the generator full load current. Now, this is an example of a thermal damage curve from one of the major manufacturers for alternators. And as you can see at the bottom, it's talking about 1, 1.2, 1.4. That would be times the full load current. So it's pretty straightforward math. And it actually, typically they have a damage curve that applies to all alternators of the same frame type. So you might have a 1500 kW and a 1750 kW that might have the same exact damage curve. It might look exactly the same. It's just that full load current changes, so it gives it different values. Now, remember that this line that's shown here is the point at which that alternator would actually be damaged. So this is a critical line to get right to make sure that we model and we don't let any of the breakers or the current exceed this value and cause damage to our units. The other curve is the decrement curve. The decrement curve is the generator fault curve. It's basically a model of what would happen if you had a fault and over time what that generator performed as. The manufacturers obviously can provide that as well, but that decrement curve is tied to the same parameters, the XD double prime and all the other different parameters that I went over earlier in the presentation. Here is the first model that we're taking a look at, the generator. If you look at, we're starting at 0 seconds, as low as possible. That's the decrement curve. The decrement curve, if you remember correctly, if you remember from our little calculation, this is the same exact engine that we did our little short calculation, which is the full load amps of the generator divided by XD double prime. And we got about 20,000 amps. So if you look here, you see 10K, and then the next line will be 20K. So this is actually starting out at right about 20,000 amps. So that would be lining up exactly with what we had calculated by hand. And you can see what it does is it decays, and then at a certain point it would reach 300% of the full load current, which would be your PMG kicking in and allowing that additional fault current to be on the system. And at some point, typically somewhere around 10 seconds, it'll intersect with the damage curve. And then the damage curve goes up, and then that's a model of the curve that we had already just shown based upon per unit values. So some of the double checks you want to do is you want to make sure the decrement curve matches the instantaneous fault that we calculated. And it's a good idea to take the manufacturer's curve and the modeled curve and put them side by side and take a look and make sure that they match. Here's an example of that. So you can see that we're about 20,000 amps on either the left side, which is the manufacturer's data, and then our model, which is the right side, which is at the outset. And then you can see how it decays, and They're not exactly the right scale, but they're decaying in the same fashion, the same way. So we know our model is good to go. So how do we coordinate with this system, with this damage and decrement curve? So what we want to do is we want to set a breaker, or possibly in some situations you can use the generator relay control that is inside the generator controllers. Some manufacturers do make very sophisticated relay modules that are inside the controllers that would do this function, and they're actually quite good at it as well. But as far as our breakers are concerned, the breaker that protects the generator, we want to allow the fault to happen for a certain amount of time, and then make sure that our breaker crosses the decrement curve, so it's on the left side of the decrement curve at some point before you get to the damage curve. So what we do is, if you look at this example, we actually, we're on the right side up until somewhere around 8 seconds, and then we jump across to the left side, which means that we're allowing the fault to happen, and we're allowing the generator to produce all that fault current until we get to that 8 seconds, and then we're protecting the generator. We're making sure that if the downstream breakers have not tripped at that point, that generator is not going to get damaged, and we're going to protect it at the generator. Where exactly that crosses is obviously an engineering judgment and decision. A lot of times it'll depend on what you have downstream and what you're coordinating with, how big your system is, and the components downstream. So this is that's pretty much a typical example of a coordination of the generator. Now we're going to add in a breaker. So here's our example situation where we had an 800 amp breaker on ATS EQ, and this was a fault. And we want to make sure that that fault is picked up by the 800 amp breaker before it gets to the 2500 amp. So you can see in this curve, the leftmost curve is an 800 amp breaker that serves the equipment branch. It's on the left side of the decrement curve the whole time, that 800 amp breaker, and it always will react before the generator breaker. But for whatever reason, if that breaker didn't work and didn't react, that generator breaker would actually be there to protect the generator before it got damaged. So I mean, that's pretty much it in a nutshell to protect generators. So let's just summarize on what we went through. The first step obviously would be to get with your manufacturers and get the alternator data sheet and some of those curves that would be applicable, and make sure you calculate the generator fault output on your own, just to double check and make sure that all your values are lining up. It's also useful to take that fault output and make sure that your fault calculations match that output, that hand math. Then you're going to have to model the decrement and the damage, and you're going to have to compare that to the manufacturer's data, and then start setting your breakers. And like I said, once you start off the top at the generator, you set that breaker, then you start setting the breakers downstream. And then that's pretty much it. So thank you very much for the opportunity to give this presentation. Michael, it's off to you.
Okay, thank you very much, Jim. That was an excellent foundation for what Dean is going to speak about next. Dean, you're on the air.
Okay, thank you, Michael. The purpose of this presentation is to increase your understanding of the properties of automatic transfer switches and how to properly apply them in healthcare power distribution systems. Application considerations include transfer switch withstand and close-in ratings, selective coordination, and finally we cover arc flash. The presented agenda defines the organization of the information I'm going to present. Many of the definitions have already been covered in Jim's presentation, so I'll go through those quickly. And then I also reference some code section articles that I'll flip through quickly, getting to the more interesting part of the presentation. I'll cover the issues relating to transfer switches and go over some of the operating characteristics of those switches. I'll walk through some typical calculations of short circuit, and then we'll get into the coordination of the emergency or essential power distribution system in healthcare facilities, and cover some of the challenges that we might encounter during that process. Okay, Jim already covered coordination, so basically this section of the code defines what selective coordination means, and this section here tells us that the emergency systems have to be coordinated. This particular article is found in 517, which is in the healthcare section of the National Electrical Code. And then this section defines what the essential electrical distribution system is, and this section defines what the critical operations power distribution system is. Some healthcare facilities may include this system. It depends on the authority having jurisdiction. It's worthwhile to check with the authority in your area to determine if some of the loads in your building fall under this branch of power or whether they can be included under the essential branch of power. And we'll cover some code sections. 727 again defines what the fact that all emergency systems need to be selectively coordinated. And then Article 517 effectively links the essential power distribution system back to Article 700, where it prescribes that the emergency power distribution system must be selectively coordinated. So this basically goes over the definitions and the codes that prescribe that the essential branches that are in healthcare buildings have to be selectively coordinated. It also goes on to state that the critical operations branch of power needs to be selectively coordinated as well. So let's move on to transfer switches and how to apply them and how to choose them in a healthcare environment. Transfer switches are tested per UL 1008, and UL 1008 defines the certain procedures for testing the switches. Many of the manufacturers publish withstand and close-in ratings for specific breakers, for any breakers, and for fuses. A specific breaker rating applies to an individual circuit breaker as manufactured by Siemens, Eaton, or any single manufacturer. And the withstand and close-in rating published by the transfer switch manufacturer applies for a very specific manufacturer of a circuit breaker. UL also recognizes that circuit breaker manufacturers will submit a list of similar circuit breakers for which the specific breaker rating will apply. Any breaker rating is a rating that applies to any circuit breaker manufactured by anybody. So those withstand and close-in ratings as published by the transfer switch manufacturers would apply for any breaker. And then you have the ratings that apply for current limiting fuses. And those are published by the manufacturers as well. So we'll go on and I'll show you a typical table published by a transfer switch manufacturer. And under the withstand and close-in ratings, these are symmetrical RMS amps that are published in this data, in this table. And a few important points to note here. One of them is that for small transfer switches, 230 amps and less, the UL listing is for 1.5 cycles of withstand and close-in, meaning that the ampere rating of the switch, say 10,000 amps, is tested at 1.5 cycles. And for switches greater than 60 amps and larger, the UL 1008 test involves testing the withstand rating at 3 cycles. And then another important point to note is that some of the withstand ratings noted in this that are published by transfer switch manufacturers are not in fact withstand ratings as defined by UL 1008. So you need to be aware that some of the published information by manufacturers is only for withstand ratings and not withstand and close-in ratings. So you just have to be sensitive to the information that's published in these tables. The other important point to note, finally, is notice how large the withstand and close-in ratings are when you apply current limiting fuses. The current limiting effect of a fuse located ahead of a transfer switch works to limit the available fault current that passes through that switch, so that when you perform the UL test, you're able to basically provide up to 200,000 amps of fault current at the source, and the transfer switch will see that value significantly less than that 200,000 because of the current limiting effect of that fuse. And I'll cover some cautions a little bit later on in the presentation about why you need to be careful when applying current limiting fuses ahead of transfer switches. So this is a summary of the parameters that you need to consider when you're specifying transfer switches. And these parameters affect the withstand and close-in ratings of transfer switches. The characteristics include the voltage, the frame size of the transfer switch, whether or not the switch is a bypass or non-bypass isolation type switch. How many number of poles do you need for your switch? Typically a switch is 3 or 4 pole. Whether or not the switch uses solid switch or overlapping neutral contacts also influences the withstand and close-in ratings. And then the type of connection to the switch, whether it's front-mounted, front and rear accessible, top connection, that type of information affects the withstand and close-in rating. So when you're specifying transfer switches, you need to identify all of these parameters either in your specs or on the single line diagram. I'd like to demonstrate some calculations that relate to fairly common system sizes that might serve healthcare facilities. This diagram shows a single utility source serving a transformer that might serve, a 2500 kVA, a 1500 kVA, or a 500 kVA transformer that's fairly typical for a small to medium-sized hospital or clinic that would be characterized as a hospital or institutional occupancy. And so based on some very simple calculations, you can see the fault current magnitudes range from somewhere between 11,000 amps and up to 53,000 amps, plus the contributions from the motors within the facility. So this is just to give you an idea of the magnitude of some of the short circuit currents that are available in an arrangement that looks like this. And then this is a configuration that you might find in a relatively large hospital environment. These transformers are arranged in a secondary spot network arrangement, and you can see that the available short circuit current jumps up considerably. It's 3 times that which is available from a single transformer. And this is also the arrangement that you might find from an urban utility. For example, here in Seattle, Seattle City Light uses secondary spot network service configurations to serve many of their buildings in downtown Seattle. And so you might be deriving your power source from one of these utility types, in which case the available fault current at the 480 volt level is quite large. And so we'll talk a little bit about what the heck does that mean with respect to your transfer switch design. And then this calculation represents something that Jim showed us already that relates to the available fault current from a generator. I used a transient reactance of 10%, but there are actual values published by the manufacturers, as Jim noted, and those are the values that should be used. But again, this just shows you that when you have a single generator, the available fault current really drops down considerably from that which is available from let's say a utility transformer, and that needs to be considered when you're selectively coordinating and choosing your transfer switches. This is a configuration that has 3 generators in parallel, and again you can see your available fault current is multiplied by 3 when you have an arrangement like this. This is something you might find in a relatively large hospital where you're not only providing power for the essential branch, but you're providing optional standby power for many other loads in the hospital as required by the owner or something like that. So then what is the engineering challenge? You have you have a code requirement that says your essential branch in a healthcare facility has to be selectively coordinated. You have high fault currents for an extended period of time because quite often you wind up eliminating instantaneous functionality on your incoming service breaker. These high fault currents available for a long period of time have to be withstood by your transfer switches and other equipment downstream of your service. You wind up with a lot of energy being transmitted through the system, so you have an issue with arc flash and how you maintain the equipment while energized and what PPE you have to wear, as well as you have to manage the cost of your design. You have to make sure that you don't need really large equipment. You have to make sure that your electrical rooms aren't really large. You're trying to control the cost of the electrical design in the project. So these are some of the challenges that you face when you're attempting to selectively coordinate and deal with the transfer switches in your system. The tools we have for selective coordination include fuses, and this is a typical curve that you might find for a Class J current limiting fuse. You have molded case circuit breakers can be used in power distribution systems to provide overcurrent short circuit protection. And then you can use insulated case or power circuit breakers that have.
So anyway, so this slide shows that we don't have selective coordination between the branch breaker and the upstream main breaker in the power panel, and we also don't have coordination in the instantaneous region between the breaker ahead of the transfer switch and the breaker serving the distribution transformer. So with a few adjustments to some of these breakers, we can manipulate the settings to a point where we do achieve selective coordination. And you can see here that the breakers in the system do selectively coordinate. And what we wind up with is we have a transfer switch that has to be able to withstand at least 38,500 amps of fault current, and that it has to be able to interrupt that current for at least 12 cycles. So this is a rating that probably is beyond that which has been tested for a 400 amp switch. Some manufacturers currently produce switches that are rated at 30 cycles. So in this particular case, we would likely have to specify that our transfer switch was able to tolerate 38,500 amps for at least 30 cycles. So this is an example of the impact that selective coordination has on the specification of automatic transfer switches. As we move forward and look at our emergency side of the circuit, consider when the circuit is served from the single generator. This set of curves demonstrates that our circuit is selectively coordinated when served with the generator. The generator itself produces a lot less fault current than the utility does. And so here you see this set of curves indicates that the system is coordinated. As Jim pointed out earlier, we had to make sure that our generator curves, our circuit breakers fell to the left of the damage curve of the generator, and it does as shown in this diagram. So a few things to point out that might help you selectively coordinate circuits. Remember to account for all the fault current degradation that occurs as the fault current transmits through your system. Account for feeder lengths, and account for the impedances of transformers and things as the system develops. Another way to coordinate systems is to use all fuses. Using fuses in your distribution system results in a real easy way to selectively coordinate. Another important tip is to use circuit breakers that have adjustable trip settings. And then eliminate redundant circuit breakers that are in your system. Two breakers that serve common loads don't necessarily have to selectively coordinate and quite often can be removed from your system. And then avoid using series-rated devices. This is a matter of two circuit breakers in series to use to provide enough AIC rating for the short circuit that might be available in your circuit, so avoid using those. Finally, a new article was written for the 2011 code that helps us manage the issues relating to arc flash. Given the fact that we have to selectively coordinate circuits and quite often we have to remove the instantaneous function of upstream circuit breakers, that means that we have a lot more energy transmitted downstream. That means that the distribution equipment is subject to a much larger arc flash rating. And so these are some concepts that have been introduced into the 2011 code that help us manage that arc flash. So with that, I'd like to pass this back to Mike.
Thank you, Dean. That was a really good presentation. I apologize to everybody for the technical difficulties that we had. We are recovering from that. What we're going to do now is we're going to take your questions, and as we answer them, please answer ours as we bring up an exit survey. We really do use these surveys to improve our webcast, so please take a minute to fill it out. And we're going to extend the time of this webcast to accommodate Q&A, so please hang in with us while we get about another 15, 20 minutes here. We got lots of good questions. And the first one's going to come from, First question is coming from George Williams from West Sacramento, and he's asking Jim question. Asking Jim, I would like an opinion on NEC 517.30, and that life safety loads can be no larger than 150 kVA.
Okay. Well, NFPA, NEC 517.30 actually says that it deals with how many transfer switches you have, and if you have a load for a building, let's say it's a small building, small hospital or small like surgery center or something like that, you would actually be able to, if you have less than 150 kVA worth of essential system loads, you can do one transfer switch. It doesn't say that life safety is limited to 150 kVA, but it says that if you have low enough load for the overall essential system, you can just do one transfer switch. Life safety is not limited, with the exception of what you can put on it by the code. But if you're over 150 kVA, you have to have one for life safety, one for critical, and one for equipment at minimum. And bigger systems would have even more than that. Thanks.
Okay. Thank you, Jim. Dean, question for you from Paul Luoma from Reston, Virginia, asking, when using a make before break ATS, do the generator and utility contributions need to be added to determine the fault current?
That's a good question. You know, in many cases, that's an ambiguous question. I think the best answer to that question is probably to ask your authority having jurisdiction. I've seen cases where you can not account for it, and I've seen cases where you are forced to account for it. And it's also, the issue is something you need to ask your electric utility, whether or not you can actually apply overlapping neutral contacts, because in many cases, utilities will prohibit you from applying them.
Okay. Thank you. Next question is for Jim, and it comes from Joe Sad, Jr. from Greenville, North Carolina, asking, is there instantaneous overlap on the TCC?
There is some instantaneous overlap on that TCC. This was in regards to one of our particular slides, where we showed the generator coordination at the end. But the other thing that I would, I don't know if we can go back to that slide, but I would note that the generator fault output, even though there is instantaneous selective coordination, instantaneous shown, the generator can only put out as much as the decrement curve. So whereas its overlap, it actually doesn't apply. So it would selectively coordinate perfectly.
Okay, thank you. Dean, Robert Mickle from Johnstown, Pennsylvania is asking, how does front versus rear affect WCR with sand closure ratings? And also, can you discuss fault current associated with closed transition automatic transfer switches?
First part first. Part 2 was answered, I think, in the previous question.
Okay.
As it relates to, do you have to account for the combined utility source and the generator source when specifying the withstand and close-in rating? I think that's a subject that's up to question with your authority, the local inspectors, and then the impact of a connection type to the close and withstand rating of a transfer. I think that's manufacturer dependent, and what you need to do is understand how you intend to connect your transfer switch to the system, how it's arranged in the electrical room and what are the possible ways that it will be connected. And then as you identify the possible manufacturers that would be qualified to bid or to supply your project, you want to make sure and review the published data from those manufacturers to understand the specific impact to the withstand and close-in rating. So from one manufacturer to another, you might have a different impact about how you physically connect the supply and load side conductors to the switch. So it kind of depends on the manufacturer as well as how you intend to connect that switch.
Okay, thank you. Jim, Randy McInnes from Fort Mill is asking, when paralleling generators for capacity and redundancy, is it common or possible to exceed the KAIC rating of the service entrance panel? How critical is this?
Is it common? Yes. I mean, is it possible? Yes. Is it common? Maybe not. But it definitely depends on what your site is. I mean, just to give you a quick example, I had a facility where we had separate service entrances from the utility with single transformers, so our fault was not that high on the utility side, but we have a single energy plant backing it up. So we had a combined parallel generator system. So our fault on the generator side was more than our utility side.
Okay. Thank you. And Dean, Phil Morissette from Auburn, Maine is asking, does current limiting breaker at ATS have the same AIC as current limiting fuses?
Well, I'm not aware of a current limiting circuit breaker I'm not aware of one that exists. A current limiting fuse is a different animal. A fuse will actually limit the amount of current that the downstream device sees, but I'm not aware of a current limiting circuit breaker. Circuit breakers with adjustable trip settings and call it variable functions can be programmed to not have an instantaneous function, and that's a common way to arrive at selective coordination, which is to turn off or not have an instantaneous function on the circuit breaker ahead of the transfer switch. But in doing that, you expose that switch to a fault current that might exceed its withstand time. So I'm not sure if that answers the question, but that's my attempt.
Okay. Hey, Jim, Paul Luoma has another question from Reston, Virginia, asking, I've been told the internal protection of the generator will de-energize the generator before the generator circuit breaker can trip. Is this true?
Some cases yes, in some cases no. I know that's ambiguous, but all the major manufacturers do have a relay inside their controllers that have a curve just like a breaker. Some of them are available even in the standard modeling software, like SCAM or something like that. You can actually get those curves and use them in your coordination plots, which I did allude to. And I know, like, for example, there's a DEC 550 from one of the manufacturers, and then the AMP Sentry from Cummins. They make and you can model them and compare them to your curve. It is important to know that information and check it, because sometimes it does conflict with your coordination study.
Okay. Thank you. And Phil Whitten from New Hampshire is asking an open-ended question saying, what do you guys consider selectively coordinated, quote-unquote, 0.1 or 0.01, et cetera? There's no definition in the NEC. I'll start with you, Dean.
You have to ask your authority having jurisdiction that question when you start working on your project. Here in Seattle, there's a movement to ignore time up to 0.1 seconds to make selective coordination a little bit easier. But right now, there is no definition, and so you would have to assume that it's from time equals 0, unless someone gives you some lenience on that.
Okay.
I would also say, I mean, in the state of Florida, 0.1 is the threshold for coordination for the Agency of Healthcare in Florida. And also there is a proposal in front of the Committee for NFPA 99, which has been approved to adopt 0.1 in NFPA 99. I don't think it's part of the official code yet, but it's in the process to get there.
Okay. Thank you very much. Let's see. Next one is going to come from, Dean. Question from Carl Becker from Myrtle Beach, South Carolina, asking, what are the typical close and latch ratings for transfer switches? I've heard 1.5 for 230 amp and above, but then 3 cycles for 60 amp and above. Please clarify.
Yeah, so in the presentation, I think the audio got a little garbled there, but it's basically 260 amps and above. Switches are tested at 3 cycles, and 230 amps and below switches are tested at 1.5 cycles. But again, I think that's manufacturer specific, and so you have to read the data from the individual manufacturer's tables. Okay.
Very good. Dean, this question is addressed to you, but maybe it's to Jim. I'm not sure. Paul Kozuik from Sherwood, Oregon is asking, did I understand that you said a PMG generator puts about 300% more current than a non-PMG? I believe you meant to say it will produce the fault current for a longer duration, not 300% or 3 times the max fault current. Please clarify.
I think that may be for me.
Yeah.
The generator will put out based upon the subtransient reactance in the initial cycles, and it'll go for a little bit, and then the PMG will kick in. And that'll kick in so that your maintained fault will not decay less than 300%. It doesn't mean that your fault is 300%. Your fault is actually a lot more than 300% at the initial phase, but it'll decay to that point and allow your breakers to trip. And typically there's another question about the time. That would be somewhere around like 0.2, 0.3. You can actually model it in the software and see what the difference is.
Okay, Very good. Thank you. And I just want to advise everybody who's listening that a corrected recording archive will be posted on the CSE website in a few days. You'll have access to the slides, the complete, uninterrupted version of the webcast, start to finish, including the Q&A. So just keep an eye out for that. Next question is for Dean. Actually, here we go. Seismic requirements for older 1982 transfer switches? Question mark, question mark, question mark. Anything to say on that, since it's coming from your turf?
Yeah. Well, I'm not exactly sure what to say, but I guess, as you design facilities, you have to be aware of the seismic criteria in the region of your building, and consider that in how you specify the switches.
Okay.
But I don't know exactly how to respond to that question.
Okay. Jim, what about the new NFPA 6-cycle rule? Do you have any comments about that?
That's the NFPA 99 0.1 threshold that we had talked about a few minutes ago.
Okay.
That's common practice in the state of Florida for the last 20 years. So, that's pretty much what we've been doing mostly here, as is.
Okay. Hey, Jim, by the way, there was a comment from Mark Rogers from Minneapolis saying that the generator curves that you were using do not seem typical of what SKM Power Tools typically shows for generators. Do you have any comment about that?
The curves that I presented in the presentation were actually we utilized SKM to make those. And SKM, just to get into the technical nature of that software, but they don't have a good way to model a PMG, so you actually have to manipulate the curve to make sure that it looks like your unit is going to perform with the PMG.
Okay, very good. Next question is from Brian Stokes from Harrisburg, Pennsylvania, asking, how does the transfer switch perform if the WCR is rated at 10 kA, assume 1.5 cycles, if the fault current available is less, such that the breaker will operate in its short-term band greater than 1.5 cycles? This is like your PE exam. Dean, you want to try that one?
Well, I guess you would, under that condition, I would say that you're misapplying the transfer switch.
Okay.
Because your circuit is exposing that switch to a condition that it's not rated to handle. I think if I'm interpreting your condition correctly. So you're saying that a switch rated for 10,000, withstand and close-in rating for 10,000 AIC, but it's going to see that for greater than 1.5 cycles. Well, you're outside the UL listed application of that switch. So in my mind, that's a misapplication. You have to revise your circuit to bring it within compliance.
Okay. We've got time for one more question or comment, and we're going to take it from Mike Wysocki from Michigan, who's asking or saying Article 705.16 indicates that, quote unquote, consideration shall be given to the contribution of fault currents from all interconnected power sources for the interrupting and short circuit ratings of equipment on interactive systems and includes generators. So by the code, do you not have to consider utility and generator when overlapping neutrals? Jim?
I was hoping you were going to say Dean, but
I think that same question has been asked 3 times now, and that's an open debate. I think a very conservative approach is to account for all of those sources when you have overlapping contacts, but I think it deserves that you just go to your authority having jurisdiction, because you would be forced to specify equipment that has a much higher rating when the probability of an occurrence of a fault during that overlapped time period the probability is probably really, really small. So I think it's a question that you need to ask your local code authorities when you start designing the systems.
Yeah, and I would agree with Dean. And it would be somewhat related and separate when you're talking about overlapping neutrals versus the syncing of the phases when you do a make versus break. So it would actually be two separate. One you might make for 5 seconds or some short amount of time. In other situations, just the neutral.
This sounds like a great topic for a technical article and consulting specifying engineer. So we'll make a note of that. With that, ladies and gentlemen, I'd like to close by thanking our fantastic speakers, Jim Ferris from TLC Engineering for Architecture and Dean Erickson from Affiliated Engineers Incorporated for generously sharing their time and expertise to the electrical engineering community. And I want to thank ASCO for sponsoring this outstanding event. We had a really good program. I'm sorry we had those technical difficulties in the middle. And with that, ladies and gentlemen, this is Michael Ivanovich signing off, and take care. See you again soon. Bye-bye.